Hello everyone. In today's video, we are going to look at the definition of discrete time Fourier series or DTFS, the synthesis and analysis equations for DTFS, and example of DTFS. Okay, so let's start with Fourier series for discrete time signals. For a periodic discrete time signal x of n with fundamental period n that's greater than or equal to 1, and the corresponding fundamental frequency omega naught equals to 2 pi over n, we can write x of n as summation of ak e to the jk omega naught n running for k values in one period. So for example, if n is equal to 4, this summation is going to run for 4 values for k. So 4 consecutive values for k. For example, again, for the example of n equals to 4, you can run it from k equal to 0 up to 3 for 4 numbers. And then ak in the above expression is equal to 1 over n sigma x of k multiplied by e to the minus jk omega naught multiplied by n. Again, this summation is going to run for uppercase n numbers. Again, for the case of n equals to 4, this can be calculated from n equal to 0 to 3 or any 4 consecutive numbers for n. And omega naught is the fundamental frequency of your periodic signal x of n. Now, equation 1 is called the Fourier series representation of x of n, and each ak value is called the Fourier series coefficient of x of n. So for a periodic signal x of n with fundamental period of n and fundamental frequency of 2 pi over n, the synthesis equation is this one, and the analysis equation is for finding is the expression that we use for finding ak values. The notation that we use is like this. We denote the Fourier series coefficient of discrete time signal x of n with a sub k. So you can use any other notation that you like. So you can use bk, ck, pk, whatever you like to represent the Fourier series coefficients of a general discrete time signal. But usually a sub k is used to represent the Fourier coefficient of x of n. Something important, which is only valid for this Fourier coefficient of discrete time signal, is that the set of ak values is periodic with period of n. In other words, after you have ak plus n is also equals to ak. So ak coefficients are periodic with period of n. So for example, if n is equal to 8, a sub 0 is going to be equal to a sub 0 plus 8 or a sub 8. So they repeat every n points. So let's look at the proof for this property, the periodicity in ak values with the period of n, which is the same period of your input, your discrete time signal. And so I have the expression for ak or analysis equation, and I want to find a sub k plus n, or I want to, for that, I can replace k with k plus n whenever I see k. I see k in here, so I'm going to substitute k with k plus n. Here it is. I substituted k with k plus n to find ak plus n, and I want to show that ak is equal to ak plus n. All right. So moving on, ak plus n is going to be equal to this summation, x of n e to the minus jk omega naught n multiplied by e to the minus j uppercase n omega naught n. All right, and here omega naught is equal to 2 pi over n. It's the fundamental frequency of your signal x of n, which is periodic with period of n. So with that, e to the minus j n omega naught n is equal to e to the minus j n multiplied by 2 pi over n, so 2 pi multiplied by n. All right, so this is the same thing that I have in here. I replace the top exponential with the bottom one, which are equivalent, because this is 2 pi. Let's rewrite it for clarity. N multiplied by 2 pi over n multiplied by small n. All right, so, and then e to the minus j 2 pi n is always equal to 1 because n here, small n in here, is an integer number. So e to the minus j 2 pi n is cosine of 2 pi n plus j times sine of 2 pi n, and cosine of 2 pi n is always equal to 1 for integer values of n, and sine of 2 pi n for integer values of n is always equal to 0. So the answer of this one is equal to 1. So basically I can substitute this exponential with 1. Doing that is going to result in this expression for a sub k plus n, which is equal to ak. So we showed that ak coefficients are periodic with period of n. All right, so now that we have the analysis equation and synthesis equation for periodic discrete time signals, we would like to solve this problem and find the Fourier coefficient of this discrete time periodic signal. Okay, so when your signals are in the sinusoidal format, it's easier to write them in the complex exponential form and then compare the components to the components of the synthesis equation and extract each ak value. And so this signal is in the sinusoidal format, and I'm going to write it in the form of complex exponentials. Let's first find the period of this signal. So I'm going to name cosine of 5 pi over 4n as x1 of n. That's going to be equal to cosine of 5 pi over 4 multiplied by n. And then I want to find the period, the fundamental period of this one. For that, I'm going to say cosine of 5 pi over 4 multiplied by small n plus uppercase n equals to cosine of 5 pi over 4 multiplied by n. As a result, 5 pi over 4 multiplied by n is equal to 2k multiplied by pi. K is an integer here. With that, let's write this one n sub 0, 1, n sub 0, 1. From here, n sub 0, 1 is going to be equal to 8. All right. For the second one, x2 of n is equal to cosine of 5 pi over 2 multiplied by n. So the same way you can find the fundamental frequency, fundamental period of this one, and if you do that, n naught 2 is going to be equal to 4. The fundamental period of this, the entire signal, I'm going to write it with n naught, is going to be equal to least common multiple of 8 and 4, which is equal to 8. All right. With that, omega naught is equal to 2 pi over 8, which is pi over 4. Right. So I'm ready to write the x of n, the given x of n, in the complex exponential form. So I'm going to use Euler formula. I'm going to write x of n is equal to 1 multiplied by e to the j multiplied by 0 plus 1 over 2 multiplied by e to the j 5 pi over 4 multiplied by n plus e to the minus j 5 pi over 4 multiplied by n plus j over 2 multiplied by e to the j pi over 2 multiplied by n plus e to the minus j pi over 2 multiplied by n. All right, so now that we have x of n in the complex exponential format, we can write the synthesis equation and compare the components of x of n with the generic synthesis equation that we have for any periodic x of n. All right, so I'm going to write synthesis equation here. That is x of n is equal to sigma in endpoints over endpoints x of a sub k multiplied by e to the j k omega naught multiplied by n, and I need to run this summation for endpoints, uppercase endpoints, which is the period, n is the period of our input signal. So we calculated n as 8. So I need to run it for 8 points on k, and I'm choosing k between -5 and 2, which is 8 points. All right, so you can choose any range that you like, but I want to compare these components with the components in the synthesis equation with the components in x of n, and I want to match the argument in complex exponentials with the argument of these exponentials. So I chose the range such that I can easily find these AK coefficients, but in general any 8 point works. All right, so I have this one in here, and then I'm going to replace omega naught with pi over 4 2. So it's sigma k equals to -5 to 2 ak e to the j k pi over 4 multiplied by n. So let me expand this summation in the synthesis equation and include all of the k components so I can easily compare it with the given x of n. So using the synthesis equation, I have x of n equals to a -5 e to the j -5 multiplied by pi over 4 multiplied by n, plus a -4 e to the j -pi times n, plus a -3 e to the j -3 pi over 4 multiplied by n, plus a -2 e to the j -pi over 2 multiplied by n, plus a -1 e to the j -pi over 4 multiplied by n, plus a 0 e to the j 0, plus a 1 e to the j pi over 4 multiplied by n, plus a 2 e to the j pi over 2 times n. All right, so I'm ready to compare these components with the ones given in the signal x of n that's provided to me. So let me draw a line in here. Okay, so I'm ready to compare them one by one, and I'm looking for this one, e to the j 0, which is this component here. So the coefficient is going to be a sub 0. So this is my a sub 0 by comparison. And then I see e to the minus j 5 pi over 4, and I see e to the minus j 5 pi over 4. And then as a result, this coefficient is a -5. All right. So moving on, I see e to the j pi over 2 multiplied by n in the given x of n, and from the synthesis equation, I have e to the j pi over 2 multiplied by n. So this is a sub 2. Okay. And then moving on, in here I see e to the minus j pi over 2 times n. And in my synthesis equation, I see it here. So that must be my a sub 2 component. So this is also a sub minus 2 term coefficient. All right, so I'm getting to e to the j 5 pi over 4 multiplied by n, and this one here. but I can't find this exponential in the synthesis equation. So, and the reason is that I need to do some manipulation on this one to find the corresponding exponential in the synthesis equation. But I can do that this way. So let's try multiplying. So I'm looking for e to the j 5 pi over 4 multiplied by n. And I didn't find the corresponding term in the synthesis equation when I chose k values between -5 and 2. One way to find the corresponding complex exponential is to multiply this e to the j 5 pi over 4n by a complex exponential whose value is equal to 1 regardless of the choice of n. And then make sure that you find the corresponding exponential in your synthesis equation. Here I can multiply this by e to the j minus j 2 pi n. This guy here is equal to 1 for any choice of n value, because n is an integer number. So if you do that, you're going to see that it's going to be equal to e to the j 5 pi over 4 minus 8 pi over 4 multiplied by n. That's going to be equal to e to the j minus 3 pi over 4 multiplied by n, or e to the minus j 3 pi over 4 multiplied by n. All right, so now you're going to see this expression in the synthesis equation. Let's take a look. It's here. Right, so this term in here is your a negative 3. With that, we found all of the Fourier series coefficients of x of n and in the given range, and we know that AK coefficients are periodic with period of 8 for this signal. So we found 8 distinct values for AK, and then these AK values are going to repeat every 8 points. So A sub 0, we found it to be equal to 1. A negative 5 was equal to 1 over 2. A negative 2 was equal to j over 2. And A negative 3 was equal to 1 over 2. Because I wanted to find the AK values in the range of -5 to 2, any AK values that I didn't find in the expression of x of n is which is within the range of -5 and 2, is going to be equal to 0. So I have -5 and -4. I didn't find a -4, so that's going to be equal to 0. I have a -3, a -2. I don't see a -1, so a -1 is going to be equal to 0. A 0 is there. A 1 also is not there, so it's going to be equal to 0. So for any cosine and sine term, you're going to find 2 AK coefficients. And for any DC term in here, for example, 1 is a DC term here, you're going to have 1 Fourier coefficient, which is going to be your A sub 0. And that this is valid for when x of n is in the format of a sinusoidal signal. All right, so I was looking for 8 numbers. 1, 2, 3, 4, 5, 6, 7. Where is A2? Did I get the value of A2? A2 also was, I missed it. A2 was equal to j over 2. All right, so now let's look at the properties of discrete time Fourier series. So these properties are provided in section 3.7 and table 3.2 of your textbook. Please review them, and in the class we're going to solve problems using these properties. But the important one of the important ones is the Parseval's relation, which I'm going to explain in here. which says for a periodic signal x of n that we can represent using the synthesis equation, 1 over n sum of magnitude of x of n to the power of 2 for uppercase n points is going to be equal to sum of the magnitude squared of ak values. So for n uppercase n points of k. So magnitude of ak squared is the average energy of the case harmonic component. And basically it says that energy of a signal is equal to sum of the energy of its harmonic components. Okay, so we are going to practice using Parseval relation as well as other DTFS properties in solving problems in the class. Thank you for watching.